Yeah, just mentioned that in the previous MRST symposium, I also gave a talk on adjoint-based sensitivity calculations in MRST. This will hopefully show that we have done a bit more than what I presented the last time. The outline of my talk, I will say a bit about model parameters and sensitivities and how they can be computed in MRST. Talk about model tuning and what kind of optimizers we can use for this purpose. Very briefly on network-based models, which is what we have been working quite a bit on since the last symposium, and I will show a few examples at the end. What kind of facilitates the model training in MRST is this model parameter class, and the basic utility for this is that it keeps track of and updates parameters for adjoint simulations and optimization. This just shows one example of one such object from the parameter class. This specific example is called SWL, which is the lower water saturation, which scales the relative probabilities. The main task of this model parameter class is to keep track of where these parameters are in our model and how to set and get parameters and so on and update them. In this, there's also this, for every class of parameters, there is this limit that are used both as bounds in our optimization, but also to scale the optimization problem. So this is just one example. So in MRST, there are a lot of default setups available for many of the common parameters, but it's also made in such a way that it should be easy to set up custom parameters if you have some particular model that you want to, and where you have some special parameters that you want to compute the sensitivities with respect to. And in this class, there is several options for setting up multipliers and looking at subsets of parameters and grouping them together and using different scalings and so on, which all can be quite important for how the optimization will run. So to compute sensitivities in MRST, you need basically two things. First, you need to set up an objective. And for model training, this will typically be a mismatch function, which takes the output from a simulation and compares it to some reference output. And to work, this objective needs to be of a special format such that it fits into the framework. And of course, the second thing you need is to set up a collection of parameters, which you set up with this parameter class. And the good thing when you're using adjoints is that you could set up as many parameters as you want. You still only need one adjoint simulation to compute the sensitivities. Briefly on model tuning, typically we consider some mismatch function that is sum of squared residuals. Now, each of these residuals is gives us the difference of output of our model and the observed or reference quantity, and they are typically also weighted because we might be comparing things that are of very different orders of magnitude. So to solve these optimization problems, we support two kinds of methods. You could either use a quasi-Newton type method or a Gauss-Newton type method. So in the quasi-Newton type method, you typically have an update, which is of the form where you have the gradient and multiply this by some representation of a matrix that should be approximation of the inverse Hessian, and what then is typically used is some BFGS formula. While in the Levenberg-Marquardt method that we also have, you use a better approximation of the Hessian, so this will typically have a faster convergence, where this approximation is built up from the Jacobian of the residuals. So at least when residues are small, this Hessian approximation is much better than what you obtain from, say, a BFGS formula. And this also includes a damping factor, because if you set up this optimization, this objective directly, this would typically be an e-post problem, so the actual Hessian would be singular. So, but this damping factor then helps us in that respect. We just mentioned that this Jacobian is dense, and it is of size equal to n theta times ny, where n theta is the number of parameters and ny is the number of observation points. Of course, we have supported adjoints for a long time, but if you want to compute this misfit Jacobian, this actually, if you're going to do it kind of in sequence, this will require many adjoint simulations. So if you're doing the adjoint, you would actually have to do ny number of adjoint simulations, where ny was this number of matching points. But as long as we're dealing with quite small models, say you have a number of parameters and a number of matching points on a few thousand, you can do this directly where we set up adjoint matrix equations. So we just solve one adjoint equation, but we solve it with multiple right-hand sides. And this works well if you're doing, as I said, a sufficiently small problem, where we're using a direct inverse solver for this part. So you can do this with a lot of different optimizers. So this just shows a test where we compared the quasi-Newton method we have in MRST and the Levenberg-Marquardt method we have in MRST to a few other optimizers from the MATLAB optimization toolbox and also the IPOpt. And basically the takeaway, most of these quasi-Newton methods perform quite equally, but we always see that this Levenberg-Marquardt method, which also is used in this MATLAB LSQ nonlin, has a much more rapid convergence. Okay, so setting up model tuning in MRST, there is at least two ways you could do this. Either we can just call the optimizer directly if we just make a function handle to our objective, and this automatically will now scale the parameters between 0 and 1 during optimization, and this kind of makes sure that that optimization runs a bit smoother. But if you set it up like this, the only output you will get is the objective value and the optimized parameters, and you don't kind of everything that is done during the optimization is lost. So one way to deal with this is that you rather could set it up in this optimization problem class, and this does the similar parameter scaling, but it also writes intermediate stages to disk. So if you're running a lengthy simulation, you can abort it and then you can continue later on. And this optimization problem class also inherits from the base ensemble class in MRST. So basically you could also run optimizations over model ensembles in this and set up this quite easily. So what we have been using these adjoint-based sensitivity calculations for is, or doing a lot of work on, is so-called network-based models. So this could be either a network that is based on a coarse grid, or it could be a interval network model, which is also quite popular. So the basic thing here is that we build a reduced order model, which has the same kind of parameters as our underlying model, but now in this reduced order sense, the parameters don't really make that much physical meaning anymore. They are just parameters to train our model. And within these coarse grid network models, we also have, we distinguish between either a partition-based, which is based on a partition of the underlying fine grid, or it could be just a very simple outline of our model. So just to show one quick example, this is some work we did for the Brygge model quite a while back, where we consider both these coarse grid networks and also these pure network models. So what it can, for instance, be used for, now that we're building a very small model, we could use this as a reduced order model in an optimization. So what we used it for here was to optimize NPV. And for this particular model, reduced order models also performed well, even though the optimized schedule is very different from the training schedule. This doesn't always need to be the case. Another example of what we did was that we built coarse grid network model for a geothermal storage plant. So in the original model there were 95 wells, which were collected into 6 manifolds. And we had temperature data for the manifolds. So what we did in the coarse model is that we just built this with 6 wells corresponding to these manifolds, and then trained this model based on the observed temperature data. And even for such a simple model, we were able to train it. The red line here shows the training, and then the yellow line shows the prediction based on the trained model. And even though conditions changed quite substantially, the model was able to predict quite well the temperatures for both the observed temperatures in the wells and in these manifolds. So I will just mention a few more things. Since we now can also compute these mismatched Jacobians, these can be used for quite a few things. And one of the things we looked into was to use this spread of sensitivities in this full Jacobian matrix as an indication of where one should refine our network model. So one can think of, if we're looking at a certain parameter and the sensitivity of this parameter with respect to an early time step tells us that it should be increased, but it might tell us that the change in this parameter should be decreased with respect to some matching point at late times. This kind of tells us that we don't have a sufficiently rich model to match our training data. And in this way, we could kind of gave us an indication of where the model should be enriched. Another use of this Jacobian is that we can look at and approximate the null space of it, because this tells us something about how rich the training data is. And if we're trying to use it for something else than the training data, we can estimate how far into this null space we're going, and then also give an estimate on how accurate our model will be for something very different than the training data. Yeah, so that was a very quick overview of some of this functionality and what we have used it for. So I think we could say that MRST has quite general and efficient tools to compute gradients and sensitivities for any kind of function with respect to any kind of parameters. There are of course limitations, but it's quite general and should be quite easy to set up. We also saw that the parameter tuning can be run with various optimizers, then both the quasi-Newton type, but for sufficiently small models, you can also use the Levenberg-Marquardt type methods. And I would also say that this, if you can compute this misfit Jacobian, it's very useful because you can do a lot of analysis based on it. But what is currently, the limitation here is that the model can't be too large because we then get this huge dense matrix. But there are kind of techniques that that use rather low rank representations for it. But this is currently not part of the MRST functionality. So with that, I would like to say thank you.